Welcome to Alum Video 3. This is the last and final video for the Alum Synthesis Lab. Today we'll be talking about what my crystals look like now, Bragg's Law, how to grow bigger crystals, what is D-spacing, and a final calculation for the D-spacing of our alum crystals. So, what do my crystals look like? Well, they actually exist, which is nice, and right now I have about 6 to 8 crystals, and one large crystal which is about 8 millimeters, while the rest are about 2 to 5 millimeters wide. All the crystals are clear and colorless and form a cubic structure. This is important because one of my crystals would make a very good seed crystal. A seed crystal can be used to grow bigger crystals, specifically one big crystal. If we were to follow the same procedure as our original alum synthesis lab, we would end up with several smaller crystals, but in order to grow a large crystal, one must get one clean jar, and they can make the same saturated alum solution as we used. If they put that solution in a clean jar and suspend a seed crystal in the solution, then all the alum will aggregate onto this crystal, and instead of growing a bunch of smaller crystals, we will get one big crystal. It is important to have a clean jar because if there is dust or any sort of particle in the solution, additional smaller crystals could be formed around them. Crystals form in layers with a certain amount of distance occurring between each layer. This is important because it can be used to calculate and determine the properties and identity of crystals. In order to calculate the spacing between crystals, we use something called Bragg's Law. Bragg's Law relates the angle of the rays diffracted from hitting a crystal, and then it also relates the distance in between each of those layers. In order to determine the calculations for our lab, we looked at the size of the peaks. Moving from right to left, we see that the peaks become more intense until they reach the most intense peak at around 2 theta equals 20 degrees. In this case, we know that n equals 4 because there are 4 intense regions or angles where the beams diffracted off of the crystal layers. We know that because the largest peak is on the left, that the other peaks represent layers that are deeper than the first layer. As you can see in my calculation, we know n equals 4, and we know 2 theta is 20, and then we plug this into Bragg's Law, knowing the wavelength is 1.54 angstroms, and we get an answer of 17.7 angstroms for the D-spacing of the alum crystal. Now for an overview of this video, we now know the D-spacing of our alum crystal. D-spacing is important because it's part of X-ray diffraction, which allows us to determine the properties and identity of certain crystals, which can be used in many different applications. Also, we did discover that our crystals had grown. This is important because we know that environmental factors like the increased temperature recently has caused more water to evaporate and the crystals to form at an accelerated rate. We also know that we can use one of these crystals as a seed crystal in order to grow a larger crystal. This is the end of my alum video 3. I hope you enjoyed it. Have a nice day.